This is Spotlight from All Things Photonics, featuring intimate sit-down conversations with preeminent figures in our industry. Unscripted, timely, and topical, this series shines the spotlight on industry-leading changemakers from all corners of the photonics landscape, from the gateways of progress to the most impactful challenges of our time.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more.
It's a subject many of us are still trying to wrap our minds around. Even if we can't all grasp its inner workings, we can still appreciate the applications it could advance to improve medical diagnostics and treatments, develop more sophisticated sensors in LIDAR, and advance computing and communications in unimaginable ways. But for all the fanfare and excitement in this field, most tangible developments go towards advancing the very same research in this field, in the hopes that we can one day get to those earlier mentioned applications. Yannick Salamin is an assistant professor with the College of Optics and Photonics at the University of Central Florida. At a young age, his interest in science, paired with a curiosity to learn more, led him to explore the quantum properties of light. In this spotlight conversation, Yannick offers a crash course on quantum nonlinear photonics, shares how his journey around the world helped expand his knowledge, and gives his best prediction as to when we could expect to see more quantum devices in our hospitals. Joining me today is Dr. Yannick Salamin, an assistant professor with the College of Optics and Photonics at the University of Central Florida. Yannick, thank you so much for giving us the time.
Thank you. Thank you for the invitation. It's a real pleasure to be here. I'm excited. This is my first podcast. So.
Oh, well, we're very happy to have you. And, you know, your research focusing on the exploration of quantum properties of light and the dynamics, nonlinear optics is certainly something worth talking about. And we know an award is helping you jumpstart a new quantum research group that you're a big part of. Could you talk to me a little bit about this research group and how those funds will be used to kind of help further its mission?
Yes, so indeed, we recently got an award, which is an award that is focused on helping junior faculty like myself to kind of kickstart their group, but also in the hopes to then get more money down the road. So it's kind of a seed money in some sense that will allow us to perform some early work that will then be used for attracting more prestigious awards or bigger projects with more money, so we can kind of keep the research funding.
Tell me more about this research group, kind of who's involved and what the objectives are with this.
Yeah, so I started about a year ago, where I essentially started the quantum nonlinear photonics group, where we have graduate students and undergraduate students, as well as research scientists or postdocs that are working in the group. We are focused on all the aspects of nonlinear photonics, and how can we use nonlinear photonics to kind of shape the properties of light, the quantum properties of light in particular. And so when I started, I was alone. The group consisted of me and myself, but then I quickly was able to recruit some students and a postdoc, which is very important and helpful to start the group because we have to build a lab. That means everything from cleaning up the old space, renovate, setting up the new optical tables, the frames, and then came the equipment, lasers, and different diagnostic tools, and slowly plan the experiment that we want to build. And so now we are actively also engaged in building those experimental systems to do the first experimental demonstrations. And so pretty quickly, I was able to recruit some undergraduate students, including from my class. So students that were taking my class were interested in my work. And so I was able to recruit some students there, and also postdoc. And a postdoc was good in the beginning to have someone with experience. Postdoc is someone who already finished a PhD and is continuing the training. And so I was able to get a person working with me, and she had really a good background that matched with my research, and she was still able to learn, different topics that I'm focused on, but was able to apply her expertise towards my research. And then, and by now I have already about 3 graduate students as well that have started in the group. They have less workload on courses, and so they are able to go, more in the lab and focus on really building the theoretical frameworks needed for the research, and also now the optical systems in the lab.
That's great. And it must be sort of rewarding to see all the young minds getting attracted to this field, whereas, you've been in quantums for a good stretch now, and you're starting to see more people kind of get attracted into this field.
Yeah, no, indeed. I mean, one reason I do my job is that we can interact with young students, and this is really rewarding. And when we see the excitement and the curiosity of students work that you're working with, which then enables me to also foster new ideas and kind of have this feedback or kind of we have exchange with students, and so I can pass on my passion, and then we can really grow the group into a very dynamic and I would say I try to foster really this idea that we want to be curious and explore anything we're interested in. So we should not be worried or afraid of exploring new things.
And going back to a ground level, it sounds like, your students have a real grasp and are getting a grasp of what we're talking about, but we've heard a lot about, quantum technology, but I want to ask, how would you explain quantum nonlinear photonics if you're talking to a 10-year-old or me, for example, who has the same grasp?
This is a very important question when scientists need to interact with the general public, and we tend to maybe overcomplicate things. So this question is very important, and I did think a little bit about as from my many years in academia. I think one way to try to explain this is you can imagine light as a little ball. And of course, light can have different colors, so we can give this ball a certain color. In this case, for example, a green color. And so if we take this ball, you take this ball and you throw it through a glass window, there will be some magic happening inside of this glass where the green ball will kind of, have an interaction with the glass. And what comes out on the other side now is essentially a red ball. But now we have the green ball that will split the energy and provide these 2 new red balls. And so if you think about it, this is really what nonlinear optics is. It's a conversion of the color from green to red. And the quantum comes in because when you have this conversion from green to red, producing 2 balls, because the total energy has to be conserved and green has more energy than red, so we need to split the green energy to red balls in 2 red balls. They share the same parent, right? The green. And so they share information, they're connected. This is what we would call quantum entanglement. And so they're connected to each other. And so if, for example, now you will take one of the ball and send it to your friend, and you keep the other ball, you can know what is the characteristic of this ball that is at your friend's house by measuring your own ball. So you can imagine that the ball, for example, has a characteristic that can be either vertical or horizontally aligned, right? If it's a football, has this oval kind of shape, right? So it can either be vertical or horizontal. And so let's say you send the ball to your friend in the vertical position, And at some point, someone comes and steals the ball from your friend, right? And this will act on the ball a rotation where the ball suddenly becomes horizontal. And so if you're measuring your ball and you find that it's horizontal, you know, oh, there was something who happened, the ball was taken away, and so you have this shared information. And that kind of leads me to this one big application of quantum communication, where we can build secure network using quantum properties of light. Because if someone will try to eavesdrop, so listen to your conversation, you will know, and you can know that you've been breached. For example, that's one for example application there.
Interesting. And tell me how you get involved in the quantum field. It's so complex. What was there some applications you were interested in or experiences you had that said, I want to dive deeper into this?
I think personally for me was, I think, more the fundamental aspects of physics. I wanted to explore this kind of unknown. What is quantum, right? And I came up a little bit from a unconventional background. I didn't start off directly in quantum. I started more from optics or nonlinear optics. And then when I transitioned to MIT, I worked with Marin Soljacic, who is a leader in quantum optics in the world. And that really allowed me to explore more deeper the quantum aspect of light, and working with his group, his graduate student and postdocs, I was able to learn a lot, everything needed to explore this new topic. So I kind of wanted or was interested in it, and so I took it to myself to learn and work with people who can also teach me. And so this is how I kind of got involved in this topic. But traditionally, a student might start from undergraduate taking some introduction to quantum mechanics, where he will learn some fundamentals, concept, and mathematics that will allow him to understand the concept. But it may take years to really understand or grasp the concepts that can be very abstract at some times, right? So maybe for me, because my background was already optics and nonlinear optics, it was a bit faster. I had already a good sense of the more classical aspect of light. But if you are an undergrad, it definitely can take some time.
Sure, I can see that. And going back to your journey, you had stops in Switzerland, China, MIT, and now of course you're at University of Central Florida. Talk to me about what all this traveling and worldly experiences, meant to you for understanding photonics and quantum technologies, and kind of maybe influencing how you think about what you're working on.
Yeah. So this actually brings an important point, is that in academia, there is a unique advantage for students to travel, in a sense that through different scholarship, exchange programs, fellowships, and so on, you can, as a student, travel and visit different countries that you may have not the opportunity otherwise. And this is exactly what happened to me. When I was a senior in undergrad, I received a scholarship to go abroad for a semester. So it's an exchange program. And among the different places that I could visit was China. Now, I traveled a lot with my parents when I was a kid, throughout Europe. We had an RV, we would go to different countries in Europe, but not too much like far, away, like to the US or Asia. And so when I was in senior and I had this opportunity to go abroad, China to me was just the complete unknown. And I thought to myself, this is the one time, an opportunity I have to really do something that maybe I will never have the chance to do. And that really, was the reason I went to China, and then I really loved it. I really liked the environment. The people were super friendly to me, and it gave me, also really the new passion, which was academia. Because as an undergraduate student, you're mostly taking classes, you do a little bit of lab work here and there, but I was not really immersed in a research. But when I went to China, I was working with graduate students on the research project, and I was fascinated by it, and I just wanted to do exactly what they do. And so the first thing that I did was I was able to get a scholarship now in China for my master's degree, which allowed me to also continue the project and the research I was involved. And so I decided to stay for my master program. And then at the end of the master, I actually got an offer from ETH Zurich. So this is again in Switzerland, where I'm from. And I felt, okay, it's closer to home, family. But ETH Zurich is also one of the top schools in the world for science and technology. So it was very hard to pass on this opportunity. And so I decided to go back and work with Jörg Leuthold, who is, again, a world expert in optical communication and optical or nonlinear integrated optics. And so this is where my journey transitioned a little bit, because in China, I focused more on microwave radar systems. You can imagine, satellite communication. And so when I went to ETH, I then transitioned more to the optical world. And that's where I learned everything about optics and photonics, specifically nonlinear photonics. That's really where my focus was. And then again, at the end of my PhD, I received a fellowship, which gave me the ability to travel again abroad, going to MIT in Boston. And so I took this opportunity, and that was really like a good, how do we say this in English?
Sort of stepping stone.
Yeah, where you can jump and it takes you higher to the next level. And so that was really something, I think for my career, a really important step. And working with the group was also really inspiring, and I was able to explore the new topics that I'm doing now, quantum nonlinear photonics. So that was really a good step. Yeah.
And is, the importance of stepping out of your comfort zone and experiencing something new, which you've clearly done throughout your career, is that something you stress on your students?
Yeah, I think that's not only important for me. I mean, if you look at my career, I always kind of evolved. And this is very important because you wanna keep learning. You wanna grow as a person, as a researcher, as a teacher, student. And so this is also important to pass on to students. And when I discuss with students, or when for example, a student approached me about joining my group, one thing, and probably the most important thing that I look for, is someone who is not only passionate but curious and wants to be involved in different research, right? And so I think this is very important because everyone can learn. Mm-hmm. Not everyone wants to put the effort and wants to learn different things, right? And I think this is very important. Grades are one thing, right? But I think more important is the motivation, the curiosity, and the passion that can then come out of this. Yeah.
And getting back to your research, what are you hoping to learn or to further discover by studying the shape of quantum properties of light?
Yeah, so this is a constant question we ask ourselves, and I ask my student as well. I think it's important that students early on also start to think about why they do what they do, right? Mm-hmm. I think the larger goal is to develop new techniques that then later on can be used in practical application. I'm not necessarily talking about next year, but down the line in the future, we are developing these quantum lights in order to allow new types of detectors or sensors that are quite important for a lot of application, from medicine to navigation. I can give you, for example, an example where if our system that we are developing of producing quantum light can work, you can then use quantum light to build sensors that are much more sensitive than current sensor. And we know that metrology or sensing is crucial in any breakthrough. If you think of medicine, imaging, diagnostics, or if you think of navigation, from the stars to GPS, we always rely on the ability to measure something, right? And so when you measure with light, there is a fundamental limit which is dictated by the noise of light itself, right? So light itself is kind of noisy. And so this is what sets the limit in any measurement you can do. What is the resolution or the sensitivity that you can measure a change, for example? And so by introducing now quantum light, we're trying to reduce the noise or fluctuation of light itself so that we can reduce increase the sensitivity or the resolution of the measurements. And so this is really the goal, is to be able to show that we can use this, not only generate quantum light and measure and characterize it, but also use it in some real application.
Interesting. And I'm sure these studies aren't without their challenges. And we know quantum light is generated within special optical cavities. Is it difficult to study what's inside this space, or to get into this area?
Yes, you can imagine a black box where you have a light inside that you want to measure. Now the problem is you cannot open the box. If you open the box, this cavity is destroyed. What is a cavity? Is essentially mirrors that can trap light, right? If you think of entering a bathroom, you've probably had this experience. You enter a bathroom, you have a mirror in front of you, and in some fancy restaurants, sometimes there is a mirror also in the back, right? And so you will see yourself now back and forth a few times. This is essentially a cavity where light is trapped. So if you position yourself exactly normal incidence to the mirror, right, you will see that suddenly you only see once of yourself. Why? Because you're blocking the light from going back and forth. So you cannot place a detector in the cavity to measure the light, and you can also not open the box or the mirror, otherwise light escapes. And so how do you actually measure? So the way we do it is you can think of this box containing, for example, if you're familiar with the Schrödinger cat example, a cat. And you want to know if the cat is alive or dead. And that's usually what the quantum state of light will be. It will be in one or the other state. And so now, to give an analogy, what we're doing, we're shaking slightly the box and we listen. Is the cat making a sound? So we know, okay, it's alive or not. Now, of course, we're not literally shaking an optical cavity, but we do something very similar where we introduce a small perturbation, a very, very small perturbation. This is a perturbation that you will never see with your human eye, but we can use detectors outside of the cavity where we send the perturbation to the cavity and we look at or measure how the cavity from outside responds. And essentially, it tells us what's inside, because depending on what's inside, it changes the way the cavity behaves and responds. And so we can then infer what's inside and study the quantum properties of light inside of the cavity itself.
So if we had a quantum physicist with Schrödinger's cat and they said, is it alive or dead? I said, all right, I'll find out. And they would have a definitive answer. The answer's there, no longer wondering. Yeah. We have a yes or no. All right.
Well, because indeed in quantum mechanics, the action of measuring collapses the quantum state into one possible eigenstate, right? And so once you measure, it is measured and it is in that state.
Interesting. And going back to beyond these measurements, can talk to me about some of the applications and the benefits that can come out of these studies or can come out of your research group. You mentioned before too, more accurate measurements that could be medical or navigation. Talk to me some more about these.
Yeah, I think at least my strong interest is really medical application. I think this is really something that can benefit the society at large. Maybe it's also related to the fact my parents are working in the medical field, but I think if you think about measuring something very small, which is, for example, magnetic fields activity in the brain, right? And so if you want to measure tiny fluctuation of the magnetic field that are produced by neurological functions, you need to have a sensor that is extremely sensitive. Now, you could either take some kind of needle with a sensor and stick it into the brain, but that's maybe not the best for the patient, right? Maybe a non-invasive and invasive method would be better. And so here the idea would be if you have a quantum sensor that is extremely sensitive to magnetic field, you could have a system that will be maybe around your head and then can still probe fluctuation of the magnetic field that are deep inside of your brain. And so that will allow for example, medical doctors to do some neurological studies of different neurological disorder like Alzheimer or Parkinson, for example. So this is, we're not yet there, and I'm sure there are already machines that can somehow do similar things, but they're usually quite bulky and really large, noisy. You can think of MRI, right? So people call this, I forgot the name, but they usually have a bad name for it because it's very loud and close to, if you're kind of enclosed in this box, you feel a bit maybe worried. So if you can have new imaging tools or diagnostic tools that are much more sensitive, you won't need these big, loud machines, right? You can kind of like make it more user friendly or patient friendly. And I think especially in diagnostics and imaging I think there's a lot that can be done with quantum sensing. You can think of early cancer detection. It's super important to maximize the chances of recovery. So having the ability, for example, to measure, right? Remember the analogy of the ball, two balls sending to your friend and one you keep. Well, you can do that in an imaging or kind of sensing system where you send one ball towards maybe the tumor, and then you are measuring the other ball. And if there is a tumor, it changes the characteristic of the ball, but you're measuring the other ball. So you're not actually going to measure directly inside the patient, but you can measure outside the ball and know what was inside, right? And this kind of technologies can really have a strong impact. Of course, this is the type of thing we're interested in. This can not only be, for medical diagnostics, but also for remote object identification, kind of radar, LIDAR systems where you want to track or identify an object in the air, for example. You can do some things like that without telling, right, that you're watching, right? If you take a laser beam and point it towards the airplane, they might see that you're looking at them. But if you do the quantum sensor version, you're not looking, right? You're only looking and detecting your red ball. The other ball is going there. It's just a light passing through, right? The person will not know it was actually being measured.
That's very interesting, and we start to see, a little bit some of the applications come to fruition. I know we saw a story the other day where a handheld device was created with a smartphone that could image and even treat with some phototherapy oral cancers. So it's starting to, come out a little bit more in developments, but not fully in regular use yet. And I want to ask you, and this is an impossible question to answer, but I'm going to ask it anyways. Like, if you can take out, your crystal ball, so to speak, and fast forward 10 years, where do you see quantum technology in just our everyday lives?
This is indeed a tricky question. I think if you, if you look realistically right now, most quantum companies will mostly develop tools for quantum research, right? So that could be a special laser that is used, for example, to interrogate trapped ions or so, right? So it's not a quantum laser. It's a laser that is, optimized to the best performance possible that is used in quantum experiments. So a lot of time it's a little bit, okay, we are doing quantum, but the product itself right now is maybe not necessarily quantum. Although a laser, one could argue, is a quantum device. But in terms of maybe a decade from now, I do think that quantum sensing metrology will be the first to really have an impact. Maybe we will start to also see some communication systems that will maybe start to have interesting application. These are based on the idea that we already have, at least in the lab, and some startup that are having really good results. So I do see that in a decade or so we can have a quantum based technologies for sensing metrology. And if you think of LIGO, which is a gravitational wave detection, they are implementing quantum light into their detection scheme. So this is a real thing. They already are using quantum light to increase the sensitivity. So this is the perfect example, like I was saying before. They have spent decades to optimize every aspect of their system to reduce any noise and vibration fluctuation, right? So from thermal, seismic, and so on. But you're left with the fundamental noise of the laser. So now the last step they need is quantum light to go even below the standard limit or this classical limit, right? So this is a perfect example. Now, this is not an application of everyday person, but those technologies that are used can be then translated in the future for more everyday life application.
Okay,
And
that's great.
maybe in a few decades, this can lead to maybe a quantum computer. This is still, I think, an open question. Yes, there are some interesting, experiments coming out almost every year. We're certainly nowhere near, what people may think we are in terms of, application of a quantum computer. But it is possible that in maybe 30 years or so there will be some universal quantum computer that could change a lot of things. Even earlier technologies could help with drug discoveries, right? Developing new medicine, things like that. Definitely will have a major impact in society.
That's great. Well, we'll keep a close eye on your research and watch as things develop, and we look forward to reading some more on that. Yannick, thank you so much for joining us.
Thank you very much for taking the time and inviting me. It was a real pleasure.